In today's system design, we are going to discuss unique ID generator, also called sequencer. So here's the pictorial diagram of assigning a unique trace ID to each event. So for example, if you're sharing a FB post or you're uploading a new video, so there's a trace ID generator and it generates IDs for event A, event B, it gets put into the storage, and when you post, there's a unique ID assigned to those events. Unique IDs are important for identifying events and objects within a distributed system. However, designing a unique ID generator within a distributed system is challenging. In the next lesson, let's look at the requirements for a distributed unique ID generation system. So here are the requirements for unique identifiers. First, it should be unique. We need to assign unique identifiers to different events for identification purposes. Scalability. The ID generation system should generate at least 1 billion unique IDs per day. Availability. Since multiple events happen even at the level of nanoseconds, our system should generate IDs for all the events that occur. 64-bit numeric IDs. We restrict the length to 64 bits because this bit size is enough for many years in future. The first solution could be UUID. A strawman solution for our design uses UUID, which stands for Universally Unique IDs. This is a 128-bit number and it looks like this whole, you can check for yourself this whole big number. It gives us about 10 to the power of 38 numbers. UUIDs have different versions. We opt for version 4, which generates a pseudo-random number. Each server can generate its own ID and assign the ID to its respective event. No coordination is needed for the UUID since it's independent of the server. Scaling up or down is easy with UUID, and this system is also highly available. Using 128-bit numbers as primary keys makes the primary key indexing slower, which results in slow inserts. A workaround might be to interpret an ID as a hex string instead of a number. However, non-numeric identifiers might not be suitable for many use cases. The ID isn't of 64-bit size, however, there's a chance of duplication. Although this chance is minimal, we can't claim UUID to be deterministically unique. Additionally, UUIDs given to clients over time might not be monotonically increasing. So as you can see in the diagram, we have clients on the left-hand side. Goes through, the request goes through the load balancer, it lands on a server, and the server generates a UUID. And each of these servers generate the UUIDs independently. The second solution could be using a database. Let's try mimicking the auto-increment feature of a database. Consider a central database that provides a current ID and then increments the value by 1. We can use the current ID as a unique identifier for our events. So as you can see in the diagram, there is a central database, and each of these servers are making requests to those databases, asking for a unique ID, and the database generates those unique IDs and returns to them independently. To cater to the problem of a single point of failure, we can modify the conventional auto-increment feature that increments by 1. Instead of incrementing by 1, let's rely on a value m, where m equals the number of database servers we have. Each server generates an ID, and the following ID adds m to the previous value. This method is scalable and prevents the duplication of IDs. The cons would be, though this method is somewhat scalable, it's difficult to scale for multiple data centers. The task of adding and removing server can result in duplicate IDs. So as you can see in the diagram, the new IDs is a function of the previous ID plus 3. The third solution could be using a range handler. Now let's try to overcome the problems identified in the previous methods. We can use ranges in the central server. Suppose we have multiple ranges for 1 to 2 billion, such as 1 to 1 million, 1 million to 2 million, and so on. In such a case, a central microservice can provide a range to a server upon request. Any server can claim a range when it needs it for the first time and if it runs out of the range. Suppose the server has a range and now it keeps the start of the range in a local machine. Whenever a request for an ID is made, it provides the local variable value to the requester and increments the value by 1. The pros of this system would be the system is scalable, available, and yields user IDs that have no duplicates. Moreover, we can maintain this range in 64 bits, which is numeric. That is pretty cool. Now, cons would be we lose a significant range when a server dies and can only provide a new range once it's live again. We can overcome this shortcoming by allocating shorter ranges to the server, although the ranges should be large enough to serve identifiers for a while. So as you can see in the diagram, on the left-hand side we have clients. They generate the request, it goes through the load balancer, lands on an application server, and then you have servers, and then you have a range handler microservice which maintains the available ranges. Now let's compare the three options that we have discussed so far, using UUID, using a database, and using a range handler. So if we map it against our kind of requirements that we laid out earlier in our discussion, so in terms of uniqueness, only range handler can confidently say that it's going to generate unique IDs. In terms of scalability, UUIDs and range handler checks out. In terms of available, all three are provide good availability. In terms of 64-bit numeric ID requirement, apart from UUID, the other tools checks out. Now, what if we have a unique ID with causality requirement? Apart from having unique identifiers for events, we are also interested in finding the sequence of these events. Let's consider an example where Peter and John are two Twitter users. John posts a comment, that is event A, and Peter replies to the John's comment, event B. Event B is dependent on the event A and can't happen before it. The events are not concurrent here. We can also have concurrent events, that is, two events that occur independently to each other. For example, if Peter and John comment on two different tweets, there's no happen before relationship or causality between them. It's essential to identify the dependence of one event over the other, but not in the case of concurrent events. Now, we could use Unix timestamps for generating unique IDs with causality requirement. Unix timestamps are granular to the milliseconds and can be used to distinguish different events. We can have an ID generating server that can generate one ID in a single milliseconds. Any request to generate a unique ID is routed to that server, which returns a timestamp and then returns a unique ID. The ability to generate an ID in milliseconds allows us to generate 1,000 identifiers per second. This means we can get around 86.4 million IDs in a day. That's less than a billion per day. So the pros of this approach is simple, scalable, and easy to implement. It also enables multiple servers to handle concurrent requests. The cons will be for two concurrent events, the same timestamp is returned and the same ID is assigned to them. This way, the IDs are no longer unique. Now, Twitter Snowflake. Now, let's try to use time efficiently. We can use some bits out of the targeted 64-bit for storing time and the remaining for other information. An overview of the division is as follows. 41 bits for your timestamp, 10 bits for your worker ID, that means node ID, and 12-bit sequence, which is a random sequence. So if we look at the time to range depletion, it will be around 69 years. The count of worker IDs will be 2 to the power of 10, that is around 1000 machines, and count of sequence numbers combinations would be around 4K. Now, a single bit is assigned as a signed bit, and its value will always be 0. It makes the overall number positive. Doing so helps to ensure that any programming environment using these identifiers interprets them as positive integers. Now, 41 bits are assigned for a milliseconds. The Twitter Snowflake default epoch will be used here, which is equivalent to number for blah blah blah. We already talked about worker number and sequence number. The worker number is 10 bits, which is around 1000 worker IDs. The server creating the unique ID for its event will attach its ID. The sequence number is 12 bits. For every ID generated on the server, the sequence number is incremented by 1. It gives us 4000 unique sequence numbers. We'll reset it to 0 when it reaches 4000. The number adds a layer to avoid duplication. The weak point of this system is its reliance on time. NTP can affect the working of the system. If the clock on the one server drifts 2 seconds into the future, other servers are 2 seconds behind. The NTP clock recognizes it and calibrates its clock. Now all servers will be aligned. However, in that drifting process, IDs could have been generated for a time that hasn't occurred yet. And now we'll have a pair of possible non-current events with the same timestamp. Lastly, the causality of our events won't be maintained. The other option could be Lamport clocks, which are a form of logical clocks. Now, in Lamport clocks, each node has its counter. All of the system nodes are equipped with a numeric counter that begins at 0 when first activated. Before executing an event, the numeric counter is incremented by 1. The message sent from this event to other node has the counter value. Then the other node receives the message. It first updates its logical clock by taking the maximum of its clock value. Then it takes the 1 cent in a message and then executes the message. Lamport clocks provide a unique partial ordering of events using the happen before relationship. We can also get a total ordering of events by tagging unique node process identifiers, though such ordering isn't unique and will change with a different assignment of node identifiers. However, we should note that Lamport clocks don't allow us to infer causality at the global level. This means we can't simply compare two clock values at any server to infer what happened before relationship. Vector clocks overcome this shortcoming. Now, vector clocks maintain causal history, that is all information about the happen before relationship of events. So we must choose an efficient data structure to capture the causal history of such events. Consider the design shown below. We'll generate our IDs by concatenating relevant information, just like Twitter Snowflake. So we'll have signed bit, that is a single bit assigned as a signed bit, and its value will always be 0. Vector clock, the 53 bits and the counter of each node. Worker number, which is 10 bits, which is around 1000 worker IDs. Now let's summarize everything. Our requirements were that IDs must be unique, it should be numerical, it should fit into 64 bits, they are ordered by date, and our ability to generate 10,000 unique IDs per second. We discussed multi-master approach using the database's auto increment feature. Instead of increasing the next ID by 1, we increase it by k, where k is the number of database servers in use. The cons of this strategy was it's hard to scale with multiple data centers, IDs do not go up with time across multiple servers, and it doesn't scale well when a server is added or removed. We discussed UUID approach. The pros was, generating UUID is pretty simple. No coordination between servers is needed, so there will not be any synchronization issues. The system is easy to scale because each web server is responsible for generating IDs that they consume. An ID generator can easily scale with web servers. IDs are 128. The cons are IDs are 128 bits long, but our requirement is 64 bits. IDs do not go up with time, and IDs could be non-numeric. Then we discussed ticket server approach, where the pros was it should be numeric IDs. It's easy to implement. It works for small to medium scale applications. The cons is a single point of failure. Then we discussed Twitter Snowflake approach, where we had like sign bit, timestamp bits, data center bits, machine IDs, and sequence numbers. And the sequence number here is the 12 bits, which gives us around 4,000 combinations. The field is 0 unless more than one ID is generated in a millisecond. On the same server, in theory, a machine can support a maximum of 4,000 new IDs per milliseconds. Hope this discussion was useful. Have a nice time. Like and subscribe for more such designs.